computer line. That's on. Let's at least get it ready here. Oh, that looks pretty good. Okay. Oh, well, we're doing it when we take a picture. Take a picture of my other class. This is for posterity. Get everybody in. Okay, let's see. I think I can get everybody in. Can everyone look up? All right. Very good. I like your sign. Okay. So let me review a little bit. So what we can do is we can review this nice result that we had from last class. It allowed us to start a good filtration. Okay, so what we're going to do today is we're going to talk about good filtrations. And so let me just recall what a good filtration was. So you have 0 contained inside of, let's see, V1, inside of V2, so forth, inside of V. So what you want is you want a filtration of G modules such that two things hold. So 1V is the union of these inclusions of G modules. And then 2, we want VI over VI minus 1 isomorphic to some H0 lambda R. So that's what a good filtration is. So what we want to do is we want to take a G module and we want to actually see when it has a good filtration. So we had a lemma here, and this lemma is going to be very useful to sort of start the bottom of the filtration. Okay, and then we'll just recursively go up and change. So let V be a G module. And lambda be in x at t plus with homomorphism from this irreducible representation into V. Okay? All right. So if G of L mu into V is equal to 0 for mu's which are less than lambda, and we have that x1 of G of V nu of so this has to be 0 for all nu. Okay? So this quantifier is for all nu and xt plus. Okay, so you want homomorphisms from lower irreducibles to be 0, and then you want the x1 with all of the Weyl modules to be 0. Okay? Okay, so that V contains a submodule isomorphic to H0 lambda. So the idea is the following. So I have this L lambda, and it's contained inside of V, inside the socket. Now we also know that L lambda appears in H0 lambda as a socket also. So the idea is with these two conditions over here, what we did was we showed that we can actually lift this amount to H0 lambda. So there's actually a lifting which goes from here to here. Right. Good. Any questions on this? Good. So now we can state the criterion, the Donkin-Scott criterion for good filtrations. That's a really good warm-up for your oral exam, right?
Yeah.
Okay, good. All right, so there. So let's G model. So, okay, so the first statement sort of says how many times so let's say V has a good filtration. How many times an H0 lambda appears in the good filtration? So if V admits good filtration, then the number of factors isomorphic to H0 lambda, which we denote by V H0 lambda. Okay, so this isn't a statement. Okay, this is just notation. Turns out to be equal to the dimension of of G V lambda into V. So what you can do is you can count the number of factors by just calculating the dimension of this Helm space. So what this says, and I'll justify this in a second, is that if you take two different good filtrations, then it's not going to depend on the filtration you take in terms of this number over here. So it's like composition factors. Your filtration, your H0s can appear in different places inside the filtration as subquotients, but the number is going to be the same. So it's well defined. That's kind of nice.
Does this have to be an analog of Jordan Holder?
Yeah, it's like Jordan Holder, except these H0 lambdas are not irreducible. Okay. But still, the series is well defined. And that's all we're saying. So B, suppose that the dimension of G of lambda V is finite dimension for all lambda. And So this actually gives you a criterion, a cohomological criterion for when a module admits a good filtration. So V admits a good filtration. Part two, if I take higher x, higher x between V lambda and V, if this is 0 for all I strictly bigger than 0, then V admits a good filtration, and vice versa. And then the third criterion is, so this is like projectivity in some sense. You know, you could sort of measure projectivity with all the x, or you can just measure it with x1. And that's what happens here too. So if I take x1 of G of V lambda V, that's equal to 0. And this has to happen, of course, for all lambda and xt plus. And this is for all lambda and xt plus also. Okay. So this is a theorem. And let me just say that this result is due independently. It's due by Steve Donkin and Leonard Scott. All right. So let's prove this. So prove. Okay. So first of all, suppose B has a good filtration. So we'll prove A first. So suppose B has a good filtration. Okay. So I'm not going to go through. It's basically you just use induction. You sort of use an inductive argument on the filtration. So I want to use sort of an inductive argument on the filtration. Okay. So for example, let's say V is just a single H0. So suppose V is just equal to H0 lambda 1, let's say. Okay. So clearly, what do we know? We know that when I take V of H0 mu, the number is equal to 0 if mu is not equal to lambda 1, and 1 if mu equals lambda 1. Okay? And then, you know, you just compare it. You just compare it to the dimension of the Hom. But we already proved something about the dimension of the Hom. It's only almost one-dimensional with an H0, right? And your answer is going to be exactly the same. So this is just going to be the dimension Hom of G of E H0. Sorry, V is H0, right? Sorry, this should be a V. V of lambda, oh, and V, sorry. Okay, so when V is equal to H0 lambda 1, then this is going to be it's going to be 0 when mu is not lambda 1 and 1 when mu is equal to lambda 1. Okay. And then what you do is, let's say you have two factors. So I'm just going to kind of give you the idea, and then you can fill in the details. So let's say my V contains two factors, H0 mu1 be H0 mu2 0. Okay. So suppose, you know, it has a good filtration and it has sort of two H0s inside the good filtration. So I can kind of write it like this, right? And then, well, let's see what happens to the HOM. So when I do the HOM of what? Let's say we take one of the V lambdas, H0 mu1, it's called V of, V of V, of V lambda H0 2. This is a 2. Okay. Let's see, the next term here is what? It's x1. But we proved that x1 between a V and an H0 is 0. So that goes to 0. Okay? So what are we saying? We're saying that this thing is additive. The dimension of this is this plus that. Okay? And then that does the job. So since this is additive on short exact sequences, we actually get this result. Okay, so that proves that part. So result follows. Because H0 G, let's see, additive. Short exact sequences like this. Okay. All right, so that proves number one. So for part A. So let's prove part B. Okay, so part B. All right, so 1 implies 2. Well, if this has a good filtration, then it has sections of the form H0 mu I, right? So on each section, the X is going to vanish, right? So what you can do is, again, use this sort of argument on sort of the composition series, or sort of the good filtration series, to prove this result. Okay. So for example, in this case up here, you know, you have something here, V, and something here, right? And so if I take x I of V lambda, well, as long as I is 0, it's going to be 0 here, it's going to be 0 here. So the middle term is actually going to be 0 also. Okay. So that sort of argument proves 1 implies 2. Use that I G of V lambda is 0 for all I bigger than 0. Okay. 2 implies 3. I think that's clear, right? Okay, so this is clear. So what we need to do is we need to prove that 3 implies 1. So let's prove that 3 implies 1. Okay, so in order to show this, what do we know? Okay. All right, so what we want to do is we're going to choose a total ordering of weights. So choose total ordering of lambda 1, lambda 2, so forth and so on. I guess I should put a 0 here, 0 on the 1. Okay. Such that if lambda I is less than lambda j, this implies let's see, I is less than j. Okay, so I want a total ordering like this. And since v is not 0, we know there exists a lambda n x plus, such that g on v lambda of v is not equal to 0. So we know there's some homomorphism that's not equal to 0. And so what you can do is you can choose a minimal one. Okay? So choose I minimal amongst this order. G v of lambda I. All right. Now, I claim that by choosing sort of the minimal one in this thing, you can actually start a filtration. Okay, so what do we know first? So let's see. Let me erase this. Well, the first thing we know is that form of L of lambda I of V is let's see, is not equal to 0. Now, the reason why we know that is that if I take something here which is less, so all the composition factors here are either L lambda I or less. But the composition factors which are less have no toms inside of it because of this minimality. So that means that when I map the V here, this goes into L lambda I, and this actually has to be injected into V. Okay. And then, so what else do we know? Well, by minimality, we know that Hom G of V lambda, V mu of V, this is 0 because we chose this to be minimal whenever mu is less than or equal to lambda I. Okay? And similarly, we know that Hom G of V mu. Same condition. And then we also have that x1 of G of V mu of V by assumption is actually equal to 0 for all u and x t plus. So the point is that we have an embedding of L lambda I inside of V, and then we have everything satisfied from the previous lemma, right? So by the previous lemma, what we know is we have this L lambda I, which injects into V, and we have an H0 lambda I here, and this thing extends inside of it. Okay, inject. X. This is the softball. It doesn't vanish, so there can't be any kernel to this map. That's why it's an injection. Okay, good. Well, that means we're in good shape. We start our filtration off. Okay, so we have start, and now we just have to kind of make sure everything is okay. So set, I guess, V1 to be equal to H0, let's say lambda I. Okay? And so we have V contained inside a capital V, right, just by this embedding down here. I could write it out as a short exact sequence like this. Okay. All right, so let's see. Okay, so now what do we want to do? Well, now let's apply the X functor over here. Okay, so if I take X1 of everything, so if I take X1 of V lambda of V1, this goes to X1 of V lambda of V, and this goes to X1 of V lambda on the quotient. Okay, but now what do we know? Well, V1 is H0 lambda I, right? So this is 0 here. Okay? And we also know that X2 is going to be 0 for that too, by the result we had before. Okay, so this is 0 also. Okay? And then by hypothesis, we know that this is actually equal to 0 too. Okay, so now we have X1 on the quotient is 0, and then we just apply the process again. So we have that X1 on V lambda of V over V1 equal to 0, and now we repeat the process. Any questions on this? All right, now we just have to finish things off. So this is sort of the main idea, is to use this lemma in order to produce this submodule which embeds inside of V. All right, now if this is a finite chain, or finite, filtration, then we're done. I mean, no terminate. So we just have to worry, sometimes you have infinitely generated modules, and so we have to kind of handle that situation. Okay, so what do we have? We have 0 equals V0 into V1, V2, so forth and so on, and that's into V. And now let's set V prime would be the union of the VI's. Okay? And this is where you use the dimension of the Hom space. So we know that the dimension of Hom G on V lambda on V prime is actually equal to the dimension Hom G of V lambda. Okay, so the reason why is because there are only finitely many Homs. Finite, because I much. So we have to reach one of them. So on this side, we have to actually reach them all. And then once we reach them all, we'll be able to do it inside of this tube. That's kind of the idea. Okay, so these are equal. And then again, what you do is you just use the long exact sequence, right? Okay, so again, I just apply the Hom factor. What is x1 of this? 0. That's because V prime has a good filtration. And so these two are the same. So that means that the homomorphism from here to here has to be equal to 0 for every lambda. So therefore, this module has to be the 0 module. Okay. So, V lambda. We saw this before. So whenever this is 0 for every single way. So this implies that. V over V prime. So therefore, these two have these. Okay, any questions on this?
Let's see, you actually get all of D out of this thing, or do you use that?
You get all of V.
Like iterating this process doesn't actually terminate at U.
Because this module here is 0. Right, that's what we show. And this module has to be 0, so this is isomorphism. Okay. Inclusion is the whole thing. Okay, good. All right, so now we get to do some fun things. Because we can apply this to various situations. Okay, so let me state a corollary. Okay, so let 0, V1, V, V2, 0 be a short exact sequence of G modules. Okay. With the dimension G of V lambda, let's see, I guess V2, finite dimensional for all lambda and xt plus. Okay, so I have a short exact sequence of G modules with this criterion. So if V1 and V2 have good filtrations, then V3 has a good filtration. So, try to prove this without any cohomology. I don't think it's so easy. But with the X criterion, you could actually prove this, right? Let me just show you the X using the X criteria. So, it's not so easy constructing a good filtration for V2, given that these two have good filtrations. So what do? So we just let lambda be an xt plus, and then we just apply the x. So we know x1 g on v lambda on v1. That's going to be 0. And then x1 g of v lambda v. Well, we don't know if that's 0 or not yet. And then we have x1 g lambda on v. I guess we do know this is 0. It has good filtration. And then finally, we have x2 of g of v lambda on v1. Okay, but again, v1 has a good filtration, so this x is going to be 0 too. Okay, so that means that this x1 has to be 0 for all v lambdas, so it has a good filtration. And so it's very nice. You can just use cohomology to actually prove this.
I think I'm confused. So are we assuming V2 has a good filtration or?
Oh, sorry. What is V3? V1 and V1. Okay. So V1 and V. So these two have good filtration. The third term in the exact sequence has a good filtration. That's what I'm saying. Okay, good. Okay, so that proves it. All right, now this can also be applied to injective model. So for lambda in xt plus, let I lambda be the injective call of the simple module L lambda. So I have L lambda here, and I have the injective module for which L lambda embeds, and this is the smallest injective module, which contains L lambda as a submodule. Okay. So that's what the injective module is. All right. So there's the theorem. So let me just put it over here. There's no room to prove things. So theorem. So let lambda be dominant weight again. And I lambda be the injective hall. Now, the first thing I could say is that I lambda has a good filtration. Okay. And so now what we can do is we can say something more about how many times an H0 lambda appears in a good filtration. H0 mu appears in a good filtration of I lambda. So if I take this multiplicity, so the number of times H0 mu appears in a good filtration, this is going to be equal to the composition factor multiplicity inside of with L lambda appearing as a composition factor inside of H0M. So this is the composition factor. You know what this is called? Okay, so it's often coined as Brouwer-Humphreys reciprocity. So this occurs in highest weight categories. Reciprocity. Maybe, you know, you kind of saw this in like category O. When you took like projective modules in category O, it has filtrations by Verma modules. And the number of times that Verma module appears in the projective is the number of times that irreducible appears as a composition vector. So it's the same idea. It's exactly the same. Okay. Now, this is not so bad to prove because we have everything set up. So let's see. Let's see the proof of that. All right, now I'm going to ask you. So how do you show a module has a good filtration?
Cohomological criterion.
Yes. Okay, so I'm going to take X, 1 of G, take a B lambda, and then I have to insert my module in here, right? I better use a different letters than I've used lambda for those. Okay, so sigma is in XT form. Okay, so I want to look at X1. Is X1 0 or not? What fact do we use?
The fact that it's the injective hole and you have different weights.
Yeah, I mean, you just need it's injected. So this is 0 because I lambda is injected. It's from your homological boundary. All right, so by the criterion, I lambda has a good filtration. So again, you know, it'd be kind of a pain to show that I lambda, you know, just bare bones that it has a good filtration. But now we could use this nice Duncan-Scott criterion and actually show it has good filtration just by using cohomology. Okay, so now let's do part B. And so here's what we do. So I'm going to look at I lambda. I'm going to look at H0 mu. Okay, so by the previous result, this is the dimension of the Hom space. Right, so the dimension of Hom of G of V mu into I lambda. I lambda. All right. Now, whenever you have the injective hull, you can measure composition factor multiplicities when you have this one inside of here. So this is actually equal to the composition factor multiplicity. Let me say why. And so this part over here basically it's because, let me put a star here. And then I'll do a little footnote, okay? So this is star. And star works because if I take this functor, G of blank of I lambda, this is exact. So it's exact because I lambda is injective. There's no higher homologies. And when I take G on L mu on I lambda, so the dimension of this is equal to the delta Kronecker lambda. Okay, this is the injective hull, so L mu is in the socle. So if lambda is not equal to mu, the homomorphism is 0. But so if lambda is equal to mu, then you just have a trivial module, or just you only have one homomorphism. So that does it. So what you can do now is you can just induct on the composition length of this using the exactness of this and then this fact to prove this result.
So why does it say next if they're not the same weight?
Because when you take I mu over here, I don't know if I raised it on the board, then the socle is just L lambda. Let me just do it. Okay, so you have this. We know this goes in, and the socle, because it's the injective hull, is precisely L lambda. Okay, so L mu cannot embed inside of I lambda if mu is not equal to lambda. All right. Okay, so you use the fact that this Hom, when you have an injective, is exact, and then you have this way to count, composition factors in a model. So this is when this module has composition length 1. And for composition length 2, you have this additivity like I proved. Okay, now we're almost done. Because the character of V mu is the same as the character of H0. So if they have the same character, they have the same composition factors. And this is because the character. Take the transpose rule, you get the same thing. Okay. So that finishes that. That finishes that. It's not so long. Okay, any questions on this? All right. Now, let's see. Should have some more notes. Okay. So in the last several minutes, I'm just going to state another theorem. And this theorem is the analog for Weyl filtrations. So you have a theory now of Weyl filtrations, so filtrations by the V's. Okay. So this is for Weyl filtrations. Okay, so here we go. So theorem. Let V be a G model. So A. So if V admits Weyl filtration, then I have a way to count the number of times V lambda occurs in a Weyl filtration. And so this is the dimension G. I have a B here. What do you think you put over here? Fill in the blank.
Just be limited.
Well, I mean, is that the way the other theorem works?
Something like that, H naught.
It's not. All right, so now you can imagine what the criterion is now. So suppose that the dimension of H0G on B of H lambda is finite dimensional for all lambda in X. Okay. Now, the following are equivalent. One, V has Weyl filtration. Two. Okay. So what do you think I put here? Good review. What do you think I put in for condition 2?
X1, and all the sides of those.
Very good. Okay, X die G. Okay, now what am I going to put in these two things?
Put H0 this time.
Good. What I put here?
About B.
Good. Okay. And well, I think you know the answer. Right? Next one. B. Zero. Okay, so the story is the same for Weyl filtrations, except you just have to, instead of the V's, you use the H0s as your testing model. Okay. So once you have these sort of testing modules, you can actually do a criterion, cohomological criterion for Weyl filtrations also. All right, so next time what we'll do is we will look at tensor products. So it turns out that if you take the tensor product of two H0s, it also has good filtration. We're not going to prove it, but I'll just state it. It's a theorem of Levine. And then we'll do a few more applications, and then we'll head into this Locke-Weyl data. Okay, any questions on this? Okay, all right, thanks.